right. Okay. So in order to make an equation balanced, we have to have the same number of atoms on both sides of the reaction arrow. Okay, so let's look at an example. So let's say we have hydrogen gas and oxygen gas combining to make water, right? So why did I write H2 instead of just H?
Because you need to know how many you have.
Because it's a gas.
It's a gas, but specifically
There's two hydrogen.
there's two hydrogens. Why? It's diatomic, right? Do you guys remember how to find the diatomics?
Have no fear of ice cold beer.
You guys remember that? Yeah? Have no fear of ice cold beer?
Mm-hmm.
Cool. So have is the hydrogen, right? Of is the O2, right? So that's why I wrote them as O2 and H2, not just H and O. Does that make sense? You guys picking up what I'm laying down?
Yeah.
Cool. So if I have hydrogen and oxygen on this side and hydrogen on oxygen on this side, what I want to do to make sure that it's balanced is get the same number of each atom on both sides of the reaction arrow. Okay? So the way that I do this is by making a little tally below the reaction arrow for each of the atoms that I'm looking at, right? So to start here, I have 2 hydrogens on this side and 2 hydrogens on this side. Everybody still cool with me?
Yeah.
Steph, you good?
Yeah. Sorry.
Cool. No worries, that's okay. So then for oxygen on this side, I have 2 oxygens over here, right? And I have 1 oxygen over here. So this is not balanced, right? My oxygens are not balanced. Does that make sense? Cool. So I have 2 over here and 1 over here, so I need more oxygens on this side, right? So the way that I get more oxygens on this side is by increasing the number of water molecules, okay? I can't change the chemical structure of water, okay? The only thing that I can do is say I have more water molecules, okay? Does that make sense, guys?
Yeah.
Cool. So now I need to do a retally, right? So I have 2 times 2. Oh, you guys can't see this. It's very annoying. Ugh. Oh, good. Cool. I'm back. So this 2 applies to the hydrogen 2 and also to the oxygen, right? So what I have is 2 times 2 is 4 hydrogens now, right? And 2 times 1 is 2 oxygens. Does that make sense?
Mm-hmm.
Cool. So now I have, oh, it's a cool video of my daughter I get to watch later. So now I have 4 hydrogens on this side and only 2 on this side, right? So what do I need to do now? How can I get, sorry?
Find the 4.
Put a what?
H.
2.
Get the H.
Yeah, exactly. I'm sorry, regime. I'm just catching you here. So you want to put a 2 in front of this hydrogen, right? So now this 2 times this 2 will give us 4 hydrogens, right? Does that make sense, guys? So now we have a balanced chemical equation, right? So now let's talk for just a second about why we need to balance a chemical equation. So I don't know if you guys have any of you guys seen Full Metal Alchemist? You guys watch anime? No.
I've heard of that one, but I haven't watched it yet.
You guys are cooler than me. That's okay. But you've heard of alchemy, right?
Yeah.
So alchemy is this idea that you can change one element into another element, right? Which is totally not a thing. It's not real, right?
Yeah.
So we're not doing alchemy when we do chemical reactions. We're doing chemistry, right? And because of that, we have this law of conservation of matter, which says... Sorry, what's up, Kevin?
Doesn't it also follow like the first law of thermodynamics?
It does, but that's a little beyond the scope of what we're doing here. So this is for my 100 class, Kevin. So this might be.
Oh,
yeah,
shit.
that's
My
okay.
bad.
That's okay.
Okay.
So Tuesday, Thursdays are when I do 200 stuff. Yeah, that's why you were like, what? Yeah.
Thank you.
No worries.
Sorry for dropping it.
No worries, it's okay. All right, so the law of conservation of matter says that matter cannot be created nor destroyed. It can only it can only change from one form to another, which is just a fancy way of saying you can't make something out of nothing, right? Does that make sense, guys?
Yes.
So by making sure that we have the same number of atoms on the reactant side as we do on the product side, we're satisfying the law of conservation of matter, which again is just saying that we can rearrange the bonds here to make new molecules, but we're not fundamentally making new matter, right? Does that make sense, guys?
Yeah.
You guys want to look at some more examples? Yeah? So, let's look at a combustion reaction, okay? So, this is a type of reaction, and there are 5 types of reactions. Let's go back to the previous one so we can talk about what kind of reaction that was. So, we had 2 things here being combined to make one thing. This is called a combination. Reaction, right? So you're combining 2 reactants to make one product, right? Okay, So combustion always has some kind of fuel burned in oxygen gas, and we form carbon dioxide gas and water vapor. Okay, so that's the general form of a combustion reaction. I like combustion reactions because they are all about burning stuff, which is obviously super fun. So, what's this guy called?
Methane? No.
It is technically called methane, but what is its name in our covalent nomenclature?
Oh, carbon tetrahydride.
Yeah, you got it. Carbon tetrahydride, exactly, right?
I was thinking of polyatomic. I was like,
No problem. Yeah, no, this is great. So this is one of the things about chemical reactions that I think is really helpful is since we've covered nomenclature, now while we're doing these chemical reactions, one of the ways that I study my nomenclature is by saying what these guys' names are as I'm going through. Does that make sense? It's annoying and it's more time consuming, but it really helps the nomenclature stick better. So this guy is also known as methane, aka natural gas. It's the thing that's making my house warm enough for me not to be freezing right now. It's also the thing that if you have a gas stove, we cook with. So we take methane and we burn it with oxygen gas. And again, our products are carbon dioxide gas and water vapor, right? In case you guys haven't started looking at this chapter, maybe you're wondering what this little guy is, right? Hopefully you've picked up that little g means gas, right? Little L, which we haven't seen too much of here, is a liquid. Little S, guess what that one is?
Solid.
Yeah. And then there's one more, which is kind of a weirdo, but it's AQ, and this means aqueous, which is just something dissolved in water.
is that last one H2O on the equation?
It is, right? So if this is H2O, normally H2O has what phase? Sorry, I'm starting to get a little sick. Liquid, yeah. But have you ever burned anything and formed water liquid?
No.
Right? Why?
Because water evaporates? Or...
Because combustions produce a lot of heat, right? And that heat vaporizes water. Exactly, Steph. You got it. Does that make sense? So combustion reactions will always have water as a product, but the water will always be in the form of a gas. Okay? So now we can do the same process we did before. We'll make our little tally of each element. Right? So we have carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. Right? So I have one carbon on this side. I have 4 hydrogens and 2 oxygens. Okay? I have 1 carbon on this side, 2 hydrogens, and 2 plus 1 is 3 oxygens. Right? So, what do you guys think we should do first to try and get this thing balanced?
Get the same amount of hydrogens?
Yeah, I love that. So let's try and get the same number of hydrogens here as we have over here. So what can we do to this guy to make it the same number of hydrogens?
Add a 2 in front of the H.
Exactly. So we'll put a 2 out here, right? Doesn't change my number of carbons, but it does change my number of hydrogens and also my number of oxygens, right? So I have 2 oxygens here, and now I have 2 oxygens here for a total of 4 oxygens. Everybody all right with me?
Yeah.
So now my hydrogens and my carbons are balanced, but not my oxygen. So what can I do to the reactant side to balance the oxygens?
Add a 2 in front of the oxygen.
Exactly right. So if I put a 2 in front of the oxygen gas here, now I have 4 oxygens, and I'm balanced. Right? Pretty okay, guys? Yeah? Would you know?
Tell us that it's a gas, liquid, or solid, or aqueous.
I will. I don't expect you guys to know what the phases are. Probably the way that you guys are going to see this, I will have the equation given, and then, you know, there's a couple of different questions that I could ask, but one of them would be what coefficients would balance this, right? And then I have like a multiple choice with like 1, 2, 2, 1, something like that, you know? And then the other type of question could be what type of reaction is this, right? Does that make sense? So, but I don't expect you guys to know necessarily what the phases are. There are a handful of exceptions to that. I think that you guys hopefully have some intuition about water being a liquid, right? And so the fact that water is not a liquid in the combustion reaction is one thing that I would like you guys to know. But hopefully that's pretty intuitive though, I think, right? Kind of. Never burned anything in May water before, right? Yeah. That would be weird. Does that make sense?
So yeah, can I ask a question?
Of course. Yeah.
So, so from combination reactions to combustion, you're always just going to tally the element, get the same number by adding whatever's needed, and then make sure it's balanced. I mean, that's just the list I've kind of made.
Yeah. Mm-hmm.
But no matter what the reaction, what kind of a reaction equation it is, you're going to do the same steps, essentially. Your goal is to balance.
The goal is always to have a balanced chemical equation. Yes, that's correct. Okay. So let's just talk about the other types of reactions really quickly. So I have the 5 types of reactions. And again, these are in your lecture packet.
Right.
Yeah, so we have combination, which has a general form of A plus B goes to C, right? Which is saying that we have 2 reactants combining to form one product, which is different from the 2 reactants. Then we have decomposition, which is just the opposite of a combination reaction. So in a decomposition reaction, we have the general form of C goes to A plus B, right? So if we go back to our reaction with water, right, from the previous page, we had hydrogen gas plus oxygen gas goes to water, right? And we said that was a combination reaction. So if I reverse this reaction, then I get a decomposition reaction, right? So if I take water and I decompose it into hydrogen gas and oxygen gas, right? That would be a decomposition. Does that make sense, guys? Cool.
Yes.
All right. So we've got combination, decomposition, combustion, which has the general form that we put up there. Single replacement. And single replacement is going to have the general form A plus BC goes to AC plus B, okay? Where this guy is an ionic compound. Okay. So let me give you an example of a reaction like that. So if we take zinc metal and we react it with copper chloride in water, we'll get zinc chloride and copper solid. Okay. This type of reaction, the single replacement reaction, is something that we're going to do in experiment 7. So that'll be the next week's experiment. Okay?
Okay.
So again, the way that you would see something like this would be if I gave you this equation, right? Could you tell me that it was a single replacement reaction? Does that make sense?
Okay.
Yeah?
Yeah.
Cool. All right. And then the last type of chemical reaction is called a double displacement. And you'll see occasionally they write replacement. I always call them displacement because I call these double Ds. So the general form of this guy is going to be AB plus CD goes to AD plus CB, okay? Where these guys are all ionic. Right? Just a quick reminder on ionic compounds. When we have an ionic compound, we always write the cation first, right? And then the anion, right? Okay. So this guy is a cation, this guy is an anion, this guy is a cation, this guy is an anion. This guy, still a cation, right? When it changes partners, right, it has to hook up with an anion, right? Because that's who it's attracted to. So I can't have AC, right? Because A and C are both cations. So I have A hooking up with D because D is an anion, right? And same thing for these guys, right? I can't have BD because B and D are both anions, right? So I have C is a cation and B is an anion, right? So I like to call this one the swing your partner do-si-do, right? Everybody's changing partners. But the only way that they can change partners is by still having cation-anion pairs on the product side, okay? So let's look at an example of that. So let's say we have sodium chloride, aka table salt, plus potassium nitrate. So this is my cation, This is my cation, right? This is my anion, and this is my anion.
Is that a 2? I'm sorry, I can't.
Which,
see.
where?
On the sodium chloride, there's something parentheses.
Sodium chloride. No, this is aqueous. Sorry.
Okay.
Little AQ. So this is saying that we have them in water. So, who's going to hook up with who on the product side?
The sodium and oxygen.
Okay, so this guy is a polyatomic ion, right? So polyatomic ions are not going to break apart, right? So this guy's name is nitrate. The whole thing is our anion. Okay? So sodium is going to hook up with nitrate, right?
Right.
Yeah. So we'll get NaNO3. And what else?
Chlorine with potassium.
Right. So we would have potassium chloride, right? Does that make sense? So again, I know this is kind of silly, but I like to go through and draw the charges just to make sure that I haven't mixed up any of my pairs. Questions about that?
Do cations? Usually, they just always go first. It's always cation to anion. So like positive to negative.
Yes. So you always have the opposites attracting. Exactly.
Okay.
Mm-hmm.
So they can switch. So to
Yes.
speak.
Mm-hmm. 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 Right. Any other questions about those?
Just on the combustion part.
Yeah.
Is that just fuel plus oxygen?
Yes. So fuel plus oxygen goes to carbon dioxide gas and water vapor. Always.
That's
The fuel source is the only thing that'll change. Does that make sense?
Oh, okay, yeah.
Yeah. So in the first example we did, methane was our fuel, but it could have been any fuel source. Usually it's a carbon hydrogen based fuel source, right? Because otherwise we wouldn't be able to balance it.
Yeah.
Okay. So then the only part of chapter 5 that we haven't looked at so far here, guys, is the oxidation and reduction, which we'll have a separate lecture for, okay?
Okay, so we should get up to like section 2?
I think that takes you through from section 5.0 to section 5.4 in terms of...
Oh, okay.
Right, so the only one that we haven't done is the last section, right? I mean, that doesn't mean that you have to be like perfectly knowledgeable about this stuff yet, but in terms of where we're at with the material, right, we'll have that one last section, which I think is probably the most challenging of this chapter, and that's the one that I think, Andrea, you were saying that you struggled with before. So we'll talk about that in more detail on Monday. Today's Wednesday? Yeah, Monday.
Okay.
Cool?
So we're gonna have a meeting on Monday?
Sorry?
We're gonna have a Zoom meeting on Monday?
Yes, so this will be every Monday, Wednesday now, okay? We'll do this from 9 to 10-ish, right?
Okay, thank you.
Yeah, absolutely. Any other questions?
I keep thinking about biology with this chemical reactions of like photosynthesis and sugar. It's funny to see this like there's way more. You know,
Yeah.
What you're thinking about.
Yeah, but we can do that now. So we can do photosynthesis, right? So photosynthesis is kind of like the opposite of a combustion reaction. So you've got carbon dioxide combining with water to form
Product of
sugar and oxygen, right?
Yeah.
Yeah.
And they're interchangeable, right? So you can like put that on the other side, essentially, right, to create something else.
Say that again?
Could you create a different product, like if it started out with sugar, right?
So I think what you're saying is
Your respiration. I don't know what I'm talking about. That was so long ago.
no, that's okay. This is really good because you're connecting dots, and I love that, right? Carbon dioxide and water form sugar, which is what makes up the cell walls in plants, right? And oxygen, which is the respiratory product of photosynthesis. Yeah. So that's great. Okay. So we could totally balance that equation too. Yep, I know. Super fun. I'll let you guys do that one on your own though.
Okay.
I'm gonna turn this off real quick. Oh.